Om Swastiastu. Hello everyone. In this video, I will explain about ferrous metal and alloys production, general properties and applications from the book Manufacturing Engineering and Technology 6th edition. Ferrous metals are iron-based alloys and they are most widely used structural materials in the world. The reasons are simple, because they are relatively low cost, available in large quantities, and they can provide a wide range of mechanical and chemical properties. They are generally classified into carbon and alloy steels, stainless steels, tool and die steels, as well as cast irons and cast steels. These materials plays an essential role in manufacturing, construction, transportation, and many other industries. In terms of applications, ferrous metal alloys are literally everywhere. They are used as sheet steel for automobiles and appliances, as plates for boilers, ships, and bridges, as structural members like I-beams and rails, and also for tools, dies, and molds. Even the small fasteners like bolts, rivets, and staples are made from ferrous alloys. To give you an example, an average passenger vehicle contains about 1200 kilograms of steel, which is about 60% of its total weight. To produce iron and steel, three main raw materials are needed. First, iron ore, which can be hematite, limonite, or taconite. The ore is beneficiated and processed into pellets. Second, coke, which is made from coal. Coke not only generates the high heat required, but also produces carbon monoxide, which is the reducing gas that converts iron oxide into iron. Third, limestone, which acts as a flux. It reacts with impurities and forms slags, which float on the molten irons and can be removed. Without these three materials, iron making is not possible. The iron making process takes place in a blast furnace. This is a huge steel structure lined with refractory bricks, about the height of a 10-story building. The charged mixture of ore, coke, and limestone is dumped at the top, and preheated air at about 1100 degrees Celsius is blown into the furnace through the tuyeres. Inside, coke reacts with oxygen to form carbon monoxide, which reduces the iron ore into molten iron. The product at this stage is called pig iron, containing about 4% carbon and various impurities. The molten metal sinks to the bottom while the lighter slag floats on top, and both are tapped out at intervals. This schematic shows the blast furnace used to produce pig iron. Iron ore, coke, and limestone are charged at the top, while hot air is blasted at the bottom. Coke acts as both fuel and reducing agents, producing carbon monoxide that reduces iron oxide to molten iron. The molten iron and slag collect at the bottom and are tapped out, while exhaust gases exit from the top. This process efficiently converts raw materials into iron for steel making. Steel making is the refining of pig iron into steel. There are several furnaces used. The open hearth furnace is older and mostly replaced today. Electric furnace use an electric arc or induction to melt scrap and produce high-quality steels. The basic oxygen furnace, or BOF, is the fastest and most common method, producing hundreds of tons in less than an hour. For the highest purity, vacuum furnaces are used, where the air is removed to avoid contamination. This technology allows us to produce different grades of steel efficiently. This figure shows three main types of electric furnace used in steelmaking. In A, the electric arc furnace melts scrap metal using high-temperature arcs between carbon electrodes. In B, The rotary furnace rotates on rollers to ensure uniform melting and mixing of the metal. And in C, the induction furnace uses copper coils to heat metals through electromagnetic induction, offering clean and efficient melting or high-quality alloys. Each type is chosen based on production scale and steelmaking requirements. This figure illustrates the basic oxygen furnace or BOF used in steelmaking. Molten pig iron from the blast furnace and scrap steel are charged into the vessel. A high-purity oxygen jet is blown through a water-cooled lens into the molten metal. Then the oxygen reacts with carbon and other impurities to form oxides, which escape as gases or combine with fluxes to form slag. This process quickly refines the iron into high-quality steel, with precise control over composition and temperature. Traditionally, molten steel is cast into ingots. These ingots may be killed, semi-killed, or rimmed steel. Killed steel is fully deoxidized and uniform, but it develops shrink-edge cavities. Semi-killed steel has some porosity but reduces scrap. Rimmed steel, usually low in carbon, has a ductile outer rim but may contain defect inside. Refining steps are often added to improve quality, especially for critical components like aircraft parts or automotive shaft. Today, ingot casting has largely been replaced by continuous casting. In this process, molten steel flows through a tundish into water-cooled copper molds, solidified gradually and is drawn downward by rollers. These provide uniform qualities, reduce porosity, and can fit directly into rolling mills. Continuous casting is cheaper, faster, and produces higher quality steels than traditional ingot casting. This figure illustrates the continuous casting process used to solidify molten steel directly into semi-finished shapes. In Part A, the molten steel from the electric furnace flows through a tundish and enters a water-cooled copper mold. The metal gradually solidifies as it moves downward, forming a continuous trend that is withdrawn by pinch rolls. This process is highly controlled with cooling water and X-ray sensors, regulating the flows and solidification rate. In Part B, the twin belt continuous casting system is shown. Here, molten metals is poured between two moving steel belts cooled by high-velocity water jets. The belts from the upper and lower surface, allowing rapid solidification into thin slabs or sheets. Continuous casting offers better quality, higher efficiency, and less waste compared to traditional ingot casting. Carbon and alloy steel are the most common ferrous metal. Alloying elements like chromium, nickel, molybdenum, and vanadium are added to improve strength, toughness, or corrosion resistance. On the other hand, residual elements like hydrogen or tin may cause embrittlement or hot shortness. There are also different design systems such as IC, SAE, ASTM, and UNS that helps engineers identify steels by compositions and properties. This table shows different steels are used based on their carbon content. The low carbon steels are soft and ductile, used for panels and pipes. Medium carbon steels are stronger, used for shafts and gear. And high carbon steels are hard and wear resistant, used for tools and springs. Alloy steels with elements like chromium and nickels are used for high performance parts such as aircraft and power components. Carbon steels are classified into three groups. Low carbon steels, also known as mild steels, are soft, ductile, and used for plates, tubes, and bolts. Medium carbon steels are stronger and used in gears, axles, and machinery parts. High carbon steels are very strong and wear resistant, suitable for springs, wire, and cutting tools. Special grade with sulfur and phosphorus are designed to improve machinabilities. This table compares different types of cast irons. Gray irons is used for engine blocks and Mesin bases because of good damping. Ductile iron offer high strength and toughness for pipes and gears. White iron is hard and wear resistant, used in mill liners. Malleable irons combines toughness with machinability for fittings and brackets. Alloy steel contain higher amounts of alloying elements, giving them high strength and toughness. High strength low alloy steel or HSLA steels combine strength with relatively low weight. They are produced by microalloying and controlled rolling. These steels are used in automobiles, bridges, and ships. Advanced grade include microalloyed steels that save on heat treatment costs, and even nanoalloyed steel under development with extremely fine grain structures. This table lists the mechanical properties of advanced high-strength steel. It shows that AHSS grades like DP, TRIP, and TWIP steels achieve much higher tensile strength than conventional steels, while steels maintain good ductility. These steels are mainly used in automotive structures for lightweight design and improves crash performance. This figure shows a comparison of different types of steel based on their tensile strength and total elongations. On the horizontal axis, we have tensile strength, while on the vertical axis, we have elongation, which represent ductility. On the left, mild steel has interstitial free steels, have relatively low strength but high ductility. High strength low alloy steel have higher strength but still maintain some ductility. Transformation-induced plasticity steel or TRIP steels and dual-phase or complex-phase steels offer a good balance of both strength and ductility. TWIP steels are especially expressive, with very high ductility combined with high strength. Finally, the martensitic steels are on the far right, with extremely high strength but very limited ductility. These charts help us understand why advanced high-strength steels are chosen in automotive and structural applications. They provide lightweight designs with both strength and formability. Ultra-high strength steel are defined as steel with tensile strength above 700 megapascal. These include gold-phase, TRIP, TWIP, complex phase, and martensitic steels. Each type offers a balance of ductility and strength. They are widely used in automotive applications to design safer yet lighter vehicles. For example, TRIP steels can transform into martensite during forming, giving excellent formability and high strength. Martensitic steels can reach up to 1500 megapascal, suitable for crash-resistant components. This figure shows how different steels are used in car body. About 59% is mild steel for general structure, while high-strength low alloy and dual-phase steels are used in critical areas like pillars, frame, and reinforcement. This steel provides strength, crash resistance, and weight reduction for safer and lighter vehicles. Stainless steels are famous for their corrosion resistance thanks to protective chromium oxide films that form on their surface. They must contain at least 10 to 12% of chromium. Austenitic stainless steel are non-magnetic and highly ductile. Ferritic steels are magnetic and cheaper but less ductile. Martensitic stainless steel are hardenable and used in cutlery and surgical tools. Precipitation hardened steel are very strong and used in aerospace. Duplex steel combine ferrite and austenite, offering high corrosion resistance for chemical and water treatment industries. This table represents the mechanical properties and common application of ferrous annealed stainless steel at room temperatures. It compares austenitic, ferritic, and martensitic grades, showing differences in strength, ductility, and corrosion resistance. Austenitic steels like 304 and 316 offer excellent corrosion resistance and are used in food processing and chemical equipment. Ferritic and martensitic steel are stronger and harder, used for cutlery, turbine parts, and automotive components. Each type is chosen based on the balance between mechanical performance and corrosion protection. Tool and die steels are essential in shaping and machining materials. They must resist wear, impact, and high temperatures. High-speed steel maintain hardness even at elevated temperatures and are used for cutting tools. Hot work steels are for forging and extrusion. Cold work steel are for stamping and shearing at room temperature. Shock-resisting steel are used where impact loads are high. Mold steel are used for plastic and rubber processing. This steel enable mass production across industries. This table summarizes the main category of tool and die steel. It includes water, oil, and air hardening steels, as well as hot work, high-speed, and shock-resistant types. Each type is designed for specific application like cutting, forming, and shaping metals, where hardness, toughness, and wear resistance are essential. This table outlines the processing and service characteristic of common tools and die steels. It compares their machinability, wear resistance, toughness, and heat rate response. These properties determine which steel is best for specific tools or dies, balancing performance, durability, and manufacturing ease. This table lists the typical tools and die materials used in various metalworking processes. It matches material like high-speed steels, carbides, and cast alloys to operations such as cutting, forming, and extrusion. Each material is selected to provide the right combination of hardness, wear resistance, and toughness for each specific process. To summarize, ferrous metal and alloys remain the backbone of modern industry. Carbon alloy, stainless steel, and tool steels each serve specific purposes. Continuous casting and refining have improved steel quality and reduced costs. HSLA and ultra-high strength steel improve strength-to-weight ratio for cars and structure. Stainless steel provide corrosion resistance, while tool steels make manufacturing possible. Together, these materials continue to support innovation in engineering and technology. This is the reference that I used to make this video. And that is all for this video. Thank you for listening. Santi Om.